Welcome to the deep dive.
Thanks for having me.
So today we're really getting into the heart of railway safety, but maybe not the part people first think about.
Right, not just the signals and the steel.
Exactly. We're talking about the people, the human architecture. I mean, what does it actually take to keep these incredibly complex, massive rail networks running safely day in, day out?
Hmm,
We hear all the time about the advanced tech, automatic train protection, sophisticated control rooms.
sure. The hardware and software.
But if the tech is so good, why does it still feel like human skill? That judgment call, the whole organizational culture, why is that still the absolute key?
Well, that's really the central question, isn't it? It's kind of a paradox in modern engineering.
How so?
Because system safety assurance, SSA, as we call it, it's not just about, ticking off items on a technical checklist for a train or a bit of track.
Okay.
It's much bigger. It's this whole integrated ecosystem. You've got the legal side, the organizational structures, and the technical aspects all working together.
An ecosystem, I like that.
Yeah, and the goal of this whole ecosystem is achieving safety, so far as is reasonably practicable, SFRP.
SFRP, right, we hear that term a lot. That's the legal benchmark, isn't it? Defining sort of how safe is safe enough.
Precisely. It defines that limit of rational investment in making things safer. You can't spend infinite money for infinitesimal risk reduction.
So our mission today is to unpack the roles, the responsibilities, the processes, basically the human machinery built to meet that SRP benchmark.
Exactly. And maybe an analogy helps here. Think of SSA a bit like air traffic control, but for the entire railway.
Okay.
You've got amazing technology, sure, radars, communication systems.
Mm-hmm.
But the safe movement of thousands of planes, or in our case, trains, relies entirely on highly disciplined expert teams.
People who know their job inside out.
Absolutely. They know their role, they respect the boundaries of their responsibility, and they maintain this constant vigilance, almost a healthy paranoia, you could say.
So the system, no matter how technically advanced, is really only as strong as the human competence managing it.
That's the bottom line. The tech enables, but the people assure.
Right. Okay, let's dive into that human architecture then. Section 1. Who's actually accountable? When something goes wrong, who carries the ultimate responsibility?
Well, at the very top, the ultimate legal accountability rests with the railway authority.
The regulator.
Exactly. Think of organizations like the ERA in Europe, the FRA in the US, or maybe the ONRSR in Australia, or the RSSB in the UK providing standards. They're the ultimate backstop.
They don't run the trains day to day, though?
No, but they set the entire framework, they define the safety policies, they mandate the kind of system architecture that's required, and they enforce the legal rules that everyone else has to follow.
So they're like the lawmakers in the high court of railway safety?
That's a good way to put it. They essentially grant the license to operate, certifying that an organization is competent to manage safety.
Okay, so they set the rules, but the day-to-day grind, the actual implementation, making sure those rules are followed on the ground, that's someone else.
That falls squarely on the rail transport operator, the RTO.
The RTO.
The RTO is the company or entity that actually holds the license to run the services, their main job. Implementing the safety management system, or SMS.
The SMS, that's their safety rulebook.
Pretty much. It's their internal Bible. It details exactly how they manage risks, how they train their staff, what they do when incidents happen, how they maintain their trains and tracks, all to meet that SFRP level required by the authority.
Now, you mentioned RTOs, but in big networks, it's often not just one company running everything, is it? There's usually a split.
Yes, that's a critical point, especially for anyone starting out in the industry.
Yeah.
It's vital to understand this split because it introduces complexity.
How does it typically break down?
You usually have the RTO divided into at least two key parts: the rolling stock operator, RSO, and the railway infrastructure manager, RIM.
RSO and RIM. So RSO is the trains.
Yep. The RSO is responsible for the trains themselves, the locomotives, the carriages, their maintenance schedules, the safety systems on board the train.
And the RIM.
The RIM manages the fixed stuff, the infrastructure. So the physical tracks, the bridges, tunnels, the signaling systems beside the track, the overhead power lines, everything the train runs on or interacts with.
Okay, so you've got one group managing the moving parts, another managing the stationary parts. I can already see potential friction there.
Exactly. There's an inherent organizational tension. The RIM often focuses on keeping the infrastructure stable, maybe planning track work, which causes disruption.
Right. They need to maintain the physical assets.
While the RSO is focused on running trains on time, fleet availability, punctuality.
Getting passengers from A to B.
Precisely. So where does safety assurance come in? It has to focus intensely on managing the risk at the interface between the two.
The interface risk, where the train meets the track.
That's where a huge amount of operational risk lives. Think about it.
Mhm.
Who's responsible if a piece of track is slightly damaged? The RIM needs to assess it, but the RSO needs to know immediately to slow down or stop trains.
So communication and coordination are paramount.
Absolutely critical. The SSA processes have to ensure that the safety management systems of both the RSO and the RIM mesh perfectly at that interface. Shared understanding, coordinated actions.
And if that fails?
Well, failures in communication or coordination at that interface are often where major accidents happen. Those gaps become system failure points.
Okay, that clarifies the operational side. But what about big changes? Say a city decides to build a whole new metro line or upgrade all its signaling. The RSO and RIM aren't usually the ones designing and building that from scratch, are they?
No, generally not. That's where the delivery authority comes in.
The project owners.
Exactly. They're the ones procuring, designing, overseeing the construction, the whole delivery of the new system or the major upgrade.
And they work with lots of other companies.
Oh, yes. They rely heavily on a whole ecosystem of suppliers and contractors. These are the companies actually building the components of the physical track circuits, writing the control software, manufacturing the train bogies, supplying the control room tech.
So does a company just supplying, say, a signaling component have a direct safety responsibility, even though they won't operate?
Absolutely. It's crucial. Their core safety obligation, usually defined in the contract, is to ensure that whatever they supply, component, subsystem, whatever is proven safe, SFARP, within its intended operating environment.
Within its environment.
Yes, they need to provide the evidence for that. This creates a chain of accountability.
How does that chain work?
The safety evidence for the component flows from the supplier.
Okay.
It gets managed and integrated by the delivery authority as part of the bigger system.
Right.
And ultimately, the whole thing must be accepted as safe by the RTO who will actually operate it.
And all under the watchful eye of the main railway authority.
All under the authority's oversight. So if a critical component fails later, you can trace that failure and the responsibility back through that entire chain. Supplier, delivery authority, RTO.
That sounds like a mountain of paperwork. Documentation, evidence, tracking.
It is. It's incredibly complex information management. And that brings us neatly to the specialists, the dedicated safety professionals who manage all this.
The safety engineers.
Essentially, yes. You have the SSA practitioners. These are often engineers working inside the RTO or the delivery authority.
What do they do?
They're the ones coordinating, driving, and documenting the safety evidence gathering. You could think of them as the authors of the safety story for the project or system.
Okay, the internal experts. But you mentioned independence being important earlier.
Critically important. That's where the independent safety assessors, or ISAs, come in.
The external auditors.
Exactly. Their job is to stand outside the immediate project or operational team. They review the work done by the SSA practitioners and the delivery teams.
To ensure
The risk controls are genuinely robust, that the evidence stacks up, and importantly, that the internal teams haven't inadvertently fallen into the trap of confirmation biases.
believing it's safe just because they designed it.
Precisely. The ISA provides that crucial, impartial check.
That concept of independence is huge. It leads perfectly into our next section, Section 2. Segregation of duties and competency. Why is separating responsibilities so fundamental?
Well, simply put, segregation is the system's built-in defense against complacency and bias.
The anti-complacency mechanism, I like that.
It's absolutely fundamental.
Yeah.
If the same people who design and build a system are the only ones signing off on its safety, well, there's a massive inherent conflict of interest, isn't there?
Yeah, you can see that. You'd be marking your own homework.
Exactly. Safety judgment needs to be impartial. It needs layers of review.
And we formalize this separation, this layering, into what you call the 3 levels of assurance. Can you break those down for us? This sounds like the core governance structure.
It is. It's a progressive system, building confidence at each stage. Level 1, Level 2, Level 3.
Okay, start us off with level 1.
Level 1 is design and implementation assurance. That's all the internal work. The engine room, you might say.
The team building it.
Yes. It includes all their internal checks, design reviews, unit testing, peer reviews within the team, internal audits, quality assurance processes, everything the delivery organization or the RTO's internal teams do themselves.
So the SSA practitioner we mentioned, they'd be leading this.
Typically, yes. The Level 1 team, often guided by the SSA practitioner, generates the vast bulk of the safety evidence reports, test results, analysis documents, compliance checklists, hundreds, maybe thousands of documents on a big project.
And they're essentially saying,
They're saying, based on our internal processes, our expertise, and this mountain of evidence we've generated, we believe this system meets the safety requirements.
okay, that's the foundation, a huge amount of work, but you mentioned bias.
Right. Level 1 work, however thorough, is inevitably influenced by project pressures, cost, schedule,
Wanting to get it finished.
and just natural internal optimism. Of course it's safe. We designed it. So that's why level 1, while absolutely necessary, isn't sufficient on its own. You need the level 2.
Level 2, independent review. This is the ISA stepping in.
Exactly. Or sometimes an equivalent team from a different part of the organization, but critically independent from the project delivery team.
What do they actually do? Do they redo all the level 1 work?
No, not usually. They don't rerun all the tests or redo the design calculations. Their role is assessment and verification of the level 1 process and evidence.
So they check the checker's work.
Kind of. They review the methodology used in level 1. Were the right standards applied? Were the people doing the work competent? Is the hazard log complete? Critically, they scrutinize the logic of the safety arguments. Do the risk reduction claims actually stack up based on the evidence provided?
So the ISA's stamp of approval means?
It essentially verifies that the level 1 work appears technically sound, complete according to the plan, and importantly, free from obvious bias. They're saying, we've reviewed the process and the evidence, and it looks rigorous. It supports the safety claims being made.
Okay, here's a tricky question, though. What happens if the ISA doesn't agree? If they say, nope, this level 1 evidence isn't good enough, doesn't that throw a massive wrench in the works for a multi-million-pound project?
Oh, it absolutely can. And frankly, it's supposed to.
Right.
If the ISA raises a significant observation, a nonconformance, the project typically cannot proceed past that stage gate until it's properly resolved.
So it forces a pause.
It forces a pause and often triggers some very intense discussions, technical debates, governance meetings. If the ISA and the level 1 team fundamentally disagree on whether a risk is acceptable or if the evidence is sufficient,
Yeah.
that disagreement has to be escalated. Up the chain it goes, potentially to the highest levels of the delivery authority or the RTO leadership.
Yeah.
Ultimately, the person accountable for owning that residual risk has to make a formal, documented decision.
So the ISA doesn't have the power to stop it indefinitely, but they have the power to force the difficult conversations right to the top.
Precisely. They ensure that significant safety concerns can't just be swept under the carpet due to project pressures. Their power is enforcing transparency and accountability.
Okay, that's level 1 and level 2. What's the final step? Level 3?
Level 3 is acceptance. This is the final gateway. It's the formal regulatory approval or accreditation.
Back to the railway authority again?
Yes, the authority, the regulator, looks at the whole package. They see the robust level 1 evidence, which has been independently verified by the impartial level 2 assessment from the ISA.
And they make the final call.
They make the final call, formally accepting the residual risk associated with putting that system into service or continuing its operation. This complete documentation trail showing competent work at level 1, independent scrutiny at level 2, and final regulatory acceptance at level 3 is what demonstrates legal due diligence.
It's a very clear chain of verification. Let's zoom back in on the SSA practitioner driving that level 1 work. What specific skills do these engineers need beyond just, say, electrical or mechanical engineering?
Good question. An SSA practitioner is really a hybrid. They need their core engineering knowledge, definitely. But they have to integrate that with a deep understanding of safety principles, governance, and even aspects of law.
So what are the key technical areas?
Number 1 is hazard management. They need to be experts in techniques for identifying hazards. Things like preliminary hazard analysis, PHA, fault tree analysis, FTA, FMEA, understanding what can go wrong and why.
Okay.
But just finding hazards isn't enough. They absolutely must be fluent in the legal and regulatory frameworks, not just reciting the rules, but understanding the intent behind them. How do you actually apply that SFAP test in a real-world engineering trade-off? That's critical.
And I guess with systems getting more complex, automated, the human element is still key.
Hugely important. Expertise in human factors is becoming absolutely essential. Understanding cognitive load, operator fatigue, designing interfaces that reduce the chance of human error, especially when humans are supervising automated systems, that's a massive field in itself.
And technically, what's the non-negotiable skill set?
I'd say RAMs, reliability, availability, maintainability, and safety.
RAMs.
Yeah.
Why are those four always lumped together?
Because they're completely interdependent. You really can't assure safety in isolation from the others.
How so?
Well, think about it. An unreliable system often becomes an unsafe system because it fails unpredictably.
Right.
A system with low availability, meaning it's down a lot, forces operators to use manual workarounds, bypass procedures, operate under pressure,
Right.
and those workarounds introduce new risks that probably weren't analyzed originally.
Okay.
And poor maintainability means fixes take longer, increasing downtime, increasing pressure, and potentially introducing errors during complex maintenance itself.
So RAMs analysis isn't just a technical calculation.
Not at all. For the SSA practitioner, it's a core part of the safety argument. It provides the data to justify design choices like specifying high reliability components or arguing for simpler, more maintainable designs. It's often an economic argument as much as a technical one.
That makes sense. So for our listeners, maybe students or early career engineers thinking about this path, getting into a senior SSA role sounds like it takes time and specific experience. Any advice?
Definitely. Understand that senior SSA leads are usually pretty seasoned engineers first.
They've done the hard yards in a specific discipline.
Often, yes. They might have spent years designing signaling systems or working on rolling stock development or maybe software engineering for control systems. You need that deep technical grounding to really understand the subtleties and potential failure modes that someone just following a safety process might miss.
So get the engineering fundamentals first.
Absolutely. Get your degree, get some solid technical experience. But if you're interested in SSA early on, look for opportunities that involve things like root cause analysis of failures, managing hazard logs, participating in safety reviews.
Practical, hands-on stuff.
Exactly. And crucially, remember, the safety community relies heavily on mentoring and continuous peer review. Find experienced people, learn from them. Never, ever do critical safety analysis in isolation, especially early in your career.
Get your work checked.
Always. Some of the best learning happens when a senior colleague pulls apart your assumptions and makes you justify your reasoning. It builds rigor.
That's really solid advice. Okay, let's move on. Section 3, the safety blueprint. We've got the people, the layers of assurance. Now let's look at the actual documents and processes, the tangible outputs. When a new project kicks off, where does the formal safety process begin?
It begins with the Safety Management Plan, usually called the SMMP or sometimes just SMP.
SME. Yeah.
If you think of the RTO's overall safety management system, SMS, as the corporate safety Bible,
Right.
then the SNMP is the project-specific constitution or the safety blueprint for that specific project or system change.
What's in it?
It lays out everything. Who is responsible for what safety tasks, roles and responsibilities, what processes will be followed, how evidence will be gathered and documented, defining the level 1 activities, how the project will interface with the independent safety assessor, level 2, what the criteria are for final acceptance, level 3.
Oh.
It sets the rules of the game for proving safety for that specific undertaking.
It's the roadmap for the entire safety assurance effort.
Precisely. And the core operational process defined within that plan, the engine that drives everything, is the hazard management cycle.
The hazard management cycle. This sounds iterative.
It absolutely is. It's a continuous loop. It starts the moment a concept is born, and technically it never really stops until the system is taken out of service and decommissioned entirely.
Wow. Okay, walk us through the steps. How does it work in practice?
Right. Step 1 is hazard identification. You start by systematically brainstorming everything that could possibly go wrong.
Using those techniques you mentioned, PHA, FMEA.
Exactly. You look at energy sources, potential conflicts, failure modes. What are the bad things that could happen with this system in its environment?
That must be really hard for brand new technology where you don't have years of incident data to look back on.
That's one of the biggest challenges.
Yeah.
Identifying novel hazards requires real expertise and imagination. You can't just rely on history.
Okay, so you've identified potential hazards. What's next?
Next comes risk assessment. For each hazard, you figure out two things. How severe would the consequences be if it happened? And how likely is it to happen? Severity and likelihood.
That gives you a measure of the risk.
It does, and that leads directly into the next step, risk reduction. This is the core engineering part. Based on the assessment, you design and implement controls to either reduce the likelihood of the hazard occurring or mitigate the severity of the consequences if it does occur, or ideally both.
So this is where you add redundancy, guards, warnings, new procedures.
All of that. Hardware changes, software logic, operational rules, training, anything that brings the risk down.
And you keep reducing the risk until
Until you reach that crucial legal benchmark we talked about, SFARP, so far as is reasonably practicable.
You have to demonstrate you've done enough.
You have to demonstrate you've applied all reasonable controls, considering the cost and difficulty versus the safety benefit. Once controls are implemented, you move to validation and verification.
Checking the controls actually work.
Yes. You test them, you inspect them, you run simulations, you audit the procedures, you gather evidence to prove the controls are effective, and the system behaves as intended with the controls in place.
Okay, hazard ID, assessment, reduction, V&V, then the system goes live.
It might, but the cycle isn't finished. The final crucial step is maintaining a live hazard log.
A live log, meaning it keeps getting updated.
Constantly. Throughout the entire operational life of the system. If a new type of incident occurs, or a component starts failing more often than predicted, or a modification is made to the system,
You go back to the log.
you must go back to the hazard log. You reassess the risks in light of the new information. You might need to identify new hazards or implement additional controls. If that log just sits on a shelf gathering dust after commissioning.
Then the safety assurance has effectively stopped.
Exactly. A static hazard log means a dormant SSA process. It has to be a living document.
That concept of the live log,
Yeah.
it really connects the design phase with the long-term operational reality.
It's probably the single most important safety artifact for managing a system over its lifetime. It's the memory and the conscience of the system's safety.
Okay, so all this work, the SMP, the hazard cycle, the evidence from levels 1 and 2, it all culminates in one key document for the regulator, right? The safety case.
Yes, the safety case, or sometimes called the Safety Assurance Report, SR. Different names, same fundamental purpose.
And that purpose is
It's the formal, traceable, auditable argument demonstrating that the system is safe to operate.
the proof of due diligence.
Precisely. It pulls together all the evidence. It shows the hazards that were identified, the risks assessed, the controls implemented, the verification that was done. It explicitly states the residual risks that remain.
Residual risks, the risks you couldn't eliminate entirely.
Yes, because you can rarely eliminate all risk. The safety case argues why these remaining risks are acceptable, why they meet the SFA criteria.
And who signs off on this?
Critically, it requires formal sign-off, usually by very senior accountable people within the RTO or delivery authority. This ensures that accepting the final risk isn't just a technical decision made by engineers in isolation, it's an explicit executive responsibility.
Wow. Okay, let's dive a bit deeper into some of that jargon that underpins the safety case, especially for our engineering listeners. SFARP, we know what it stands for. But in practice, how do you judge if the cost of an extra safety measure is grossly disproportionate to the safety benefit? That sounds ethically fraught.
It can be, and it requires a very structured, often quantitative approach. It's not just a gut feeling.
So how does it work?
When you're looking at a residual risk, you ask, is there another reasonably practical control we can implement? If the answer is yes, you then have to evaluate it. What's the cost in time, money, complexity of putting that control in place?
Okay.
And then what's the magnitude of the risk reduction you'd achieve? How much safer does it make the system? This often involves complex calculations, sometimes even putting a value on preventing a fatality or serious injury based on established societal or legal benchmarks.
The value of a statistical life?
Sometimes, yes.
Yeah.
Well, that's controversial. But the core principle is, if the cost of implementing that additional safety measure is huge, enormous, grossly disproportionate compared to the small amount of risk reduction it actually achieves,
Then you've likely hit the SFA limit.
then you can argue, legally and ethically, that you've done what is reasonably practicable and further investment isn't required.
So it's not about achieving zero risk, which is impossible anyway.
No, it's about making intelligent, justified decisions on where to focus safety resources to get the biggest bang for your buck in terms of risk reduction. It forces engineers to think like economists and lawyers sometimes, justifying their choices against that legal standard.
Okay, next term, RAMs. We know reliability, availability, maintainability, safety. You said they're interdependent. How does RAMs analysis become a governance tool in SSA?
Because RAMS provides the objective data that underpins much of the Level 1 safety evidence.
Can you give an example?
Sure. Let's say you're designing a critical signaling interlock that prevents trains colliding. Your safety analysis determines it needs extremely high reliability. The RAMS analysis then calculates the required mean time between failures, MTBF, for the components.
Right.
That MTBF figure then becomes a hard requirement in the specification for the supplier. It dictates the quality of components, the level of redundancy needed in the design. The RAMS figures drive the engineering.
And availability and maintainability.
Same thing. If RAM's analysis shows a component needs frequent maintenance, low maintainability, that impacts the RTO's ability to keep the system available. Maybe longer maintenance windows are needed, reducing overall line capacity or forcing risky nighttime work. These RAMs figures become key points of negotiation and agreement between the supplier, the delivery authority, and the eventual operator. They're written into contracts.
So RAMs isn't just design data, it's contractual and operational data, too.
Exactly. It's the technical language of system performance and dependability, which is inseparable from safety.
Got it. Final bit of core jargon. SEL, safety integrity level. This sounds important for engineers designing safety systems. What does SI actually mean in practice?
SL is crucial. It comes from international standards like IEC 61508 or the railway-specific EN 50129. It's basically a measure of the required performance or reliability of a safety function.
It's a safety function, like applying the brakes automatically.
Exactly. Or ensuring a level crossing barrier comes down correctly. SL provides a graded requirement from SL1, lowest integrity, up to SL4, highest integrity.
And how do you determine what SIL level is needed?
It's based on the risk. You assess the potential consequences if that safety function fails. If failure could lead to multiple fatalities, like the automatic braking system failing on a high-speed train, you'll need a very high SIL, typically SI4. If the consequence is less severe, maybe a minor incident or slight injury risk, like a non-critical door indicator light failing, a lower SIL, maybe SIL1 or SIL2, might be sufficient.
So SIL is basically a target for how reliable that safety function needs to be.
It's more than just reliability. It's about the integrity of the entire process used to design, build, test, and maintain that function. The higher the SIL, the more rigorous everything has to be.
More checks, more testing, more documentation.
Exponentially more. For SIL4 systems, the level of rigor in design, coding standards, verification, validation, handling of modifications, it's incredibly stringent. You need mathematical proof, exhaustive testing, formal methods sometimes.
And how do you prove you've met the required SIL? You mentioned the V model earlier.
Yes, the V model is the classic representation of the verification and validation V&V process used, especially for high SIL systems.
How does it work?
Imagine a V shape. On the left, going down, you have the decomposition of requirements from high-level system requirements down to detailed component design and code.
Okay.
On the right side, going up, you have the integration and testing phases from unit testing individual components up through subsystem integration testing to full system validation against the original requirements.
And the V connects them.
Exactly. Each level of testing on the right side verifies or validates the corresponding level of design or specification on the left side. It provides that crucial traceability, proving that every single requirement has been tested and met, and that the system as a whole performs as specified, achieving the required SIL. For CL4, that traceability has to be absolutely meticulous.
That makes the rigor very visible. Okay, we've covered the blueprint.
Yeah.
Just quickly circling back to the independent safety assessor, ISA, you said they need domain expertise, like a signaling expert for a signaling project. How do you ensure that deep knowledge doesn't compromise their independence? Don't they risk getting too close?
That's a constant balancing act. The independence is primarily maintained through organizational and contractual separation.
How so?
The ISA team cannot report within the same management structure as the project team they're assessing. They must be demonstrably separate, often a completely different company or a firewalled internal unit. Financially, they must be independent too. Their payment shouldn't depend on signing off the project quickly.
But they still need the expertise.
Absolutely. An ISA without deep technical knowledge of the specific system wouldn't be credible. They wouldn't know what questions to ask or where the real risks might lie. You need that signaling subject matter expert, SME, assessing the signaling safety case.
So how do they remain objective?
The key is that the expert ISA applies standardized objective assessment methodologies. They're auditing against the requirements of the SNMP, checking the rigor of the SARP arguments, verifying the completeness of the V&V evidence. They are expert auditors using their technical knowledge to probe, not shadow designers imposing their own preferences. It's a subtle but crucial distinction.
Okay, that clarifies the role. Now let's move into Section 4, real-world lessons. Theory and process are one thing, but the metal meets the rails in the real world. Sadly, sometimes things go catastrophically wrong. What can major failures teach us about weaknesses in the human SSA system?
We really have to talk about the tragic head-on collision in Tempe, Greece in 2023. 57 people lost their lives. It's a devastating example.
And the investigation pointed away from just simple equipment failure, didn't it?
Primarily, yes. While there were issues with the implementation and operation of the modern signaling system, ETCS, the core failure was identified as being deeply rooted in organizational culture and procedural weaknesses.
What kind of weaknesses?
A long-standing tolerance, it seems, for operating sections of the network without the required technological safeguards fully functional or consistently used. Basic communication protocols weren't robustly followed. The safety management system appeared weak, and critical human factors, like managing workload and preventing errors under pressure, weren't adequately addressed.
So a manual error occurred.
Yes, the station master apparently routed the trains onto the same track, a terrible error. But that error should have been caught or mitigated, either by the ETCS technology if it had been fully operational and relied upon, or by fail-safe communication procedures, which also seem to have failed.
What's the big takeaway from Tempe regarding SSA?
It's a stark, tragic reminder that even if you have advanced safety technology, if the safety culture allows rules and procedures to be bypassed or ignored, the technology becomes almost irrelevant. The human and organizational layers of the SSA system failed profoundly.
Culture eats strategy for breakfast, as they say.
Or, in this case, culture undermined safety systems. Now, let's look at another case. The Wallen derailment in Australia 2020. This one highlights a different kind of organizational failure.
What was the issue there?
Wallen really shone a light on failures in managing contractor safety.
Going back to the RTO's responsibility for suppliers.
Exactly. The derailment, which sadly involved fatalities, was linked to work being done on the track infrastructure by a third-party contractor. The investigation found significant failures in safety communication between the infrastructure manager, RIM, and the contractor.
So the RIM's own safety system didn't adequately cover the contractor's work.
Essentially, yes. The RIM safety management system didn't have effective processes for monitoring, auditing, or controlling the safety aspects of the contractor's activities on their network. Risks were introduced by the work, but they weren't properly identified, logged, or managed within the RIM's overall safety framework.
What's the lesson for engineers there?
It's crystal clear. You cannot outsource accountability. Even if you hire a contractor to do work, the RTO, in this case the RIM part, retains the ultimate responsibility for ensuring that work is done safely on their network. Your SSA processes, your SMS, must extend to cover and control the risks introduced by all third parties working on your system.
Okay, those are sobering examples of failure. Let's flip the coin. Where have we seen rigorous SSA discipline lead directly to success?
Well, a really good example of applying SSA well on a major new project is the development of the Sydney Metro in Australia. It was a greenfield project, building a new automated metro system.
What did they do particularly well?
They embedded a very rigorous, continuous verification and validation process right from the start. They didn't treat safety assurance as something you just do at the end to get sign-off.
They used that Lite Hazard Log concept effectively.
Very effectively. The hazard log was constantly reviewed and updated. Safety issues identified during design or testing weren't just noted. They forced tangible changes to the design, the software, or the planned operating procedures throughout the entire development lifecycle. They tackled risks proactively.
And did this pay off when the system actually started running?
Reports suggest it absolutely did. They achieved some impressive operational performance targets very quickly after launch, including hitting a 98% on-time running target. Many attribute this smooth entry into service, in part, to that relentless SSA discipline during development. By mitigating risks before opening day, they reduced teething problems, improved initial reliability, and built confidence.
So upfront investment in SSA paid off in operational performance.
That's the argument, yes. And another system often cited globally for its safety and reliability is the MTR in Hong Kong.
What's their approach?
The MTR has a very mature, deeply embedded lifecycle safety management framework. They use frequent formal reviews called project safety reviews, PSRs, at key milestones throughout any project or major change.
Formal gate reviews.
Yes, very formal. It's a combination of strong regulatory oversight from the government there, coupled with a very high level of internal safety competency within the MTR itself. Their SSA practitioners are highly experienced, and safety assurance is seen as an ongoing operational necessity, not just a project hurdle.
It sounds like a deeply ingrained culture.
Very much so.
Yeah.
Now, if we zoom out and look at the global picture, the safety statistics for railways in many developed regions are actually quite good, aren't they?
Generally improving, yes.
Generally, yes. In the European Union, for example, rail has one of the best safety records of any transport mode, and the overall trend for significant accidents and fatalities has been downwards for years.
Why is that?
A large part of that is attributed to the widespread deployment of mandatory, standardized train protection systems like ETCS across borders, combined with strong, harmonized regulations enforced by bodies like the ERA and national authorities, technology and regulation working together.
What about elsewhere, like North America?
Similar trends in some ways. The overall train accident rate in the U.S., for example, has dropped significantly over the last couple of decades. The internal safety systems are working better.
There's always a but.
The but is when you look at the fatalities. The statistics often tell a more complex story about where the biggest remaining risks lie.
Oh, so?
In the U.S., for instance, the overwhelming majority of rail-related fatalities, something like 95% or more, aren't actually passengers or crew involved in train-on-train collisions or derailments caused by internal failures.
Where are they happening then?
They're happening at grade crossings, where roads cross tracks and due to trespassing on railway property.
So the interface with the public.
Exactly. It shows that while the technical SSA within the railway's operational bubble might be quite strong and improving, the biggest life safety challenge is now managing that external interface.
What does that mean for SSA?
It means the focus of SSA and human factors expertise needs to expand. It's not just about train control systems anymore. It's about public education campaigns, better infrastructure design like fencing or grade separation projects, advanced sensors and warnings at crossings, maybe even using AI to detect trespassers. The safety boundary is pushing outwards.
That's a really interesting shift, moving safety from the train driver's cab to the wider community interface. And that leads us perfectly into our final section, Section 5, Industry Trends and Future Challenges. This digital shift is huge. How are things like AI and IoT changing the actual job of an SSA practitioner?
Profoundly. The skill set is evolving rapidly. Traditionally, SSA might have focused heavily on mechanical systems, electrical circuits, civil engineering aspects. Now, it's increasingly about data, software, and connectivity.
How is IoT being used?
We're seeing widespread use of IoT sensors on trains, on tracks, on bridges, collecting vast amounts of real-time data about asset condition.
For predictive maintenance?
Exactly. Using AI algorithms to analyze that data allows for much smarter predictive maintenance. Instead of fixing things on a schedule or after they break, you can anticipate a potential failure, say in a wheel bearing or a track switch, weeks or months in advance.
That sounds like a huge safety benefit.
Potentially, yes. It allows for proactive intervention. So the SSA role now includes validating not just the physical components, but also the reliability and safety of the AI models making those predictions.
Whoa, okay. How do you assure the safety of an AI model, especially one that might be learning and changing over time? That sounds incredibly difficult compared to assessing a physical component.
It is incredibly difficult,
Yeah.
and it's one of the biggest challenges facing the industry and regulators right now. Certifying AI or machine learning systems for safety-critical functions that might need to meet a specific SIL requirement, requires totally new approaches.
Why? What's different?
Well, traditional SSA, particularly for software, often relied on deterministic logic. If input A happens, output B must follow. We could verify that logic exhaustively. But many modern AI systems rely on statistical correlations, probabilities, pattern recognition. They learn from data. Proving that such a system will always behave safely and predictably, especially when faced with unexpected or novel situations it wasn't explicitly trained on, is much, much harder.
So what's needed?
We need new standards, new validation techniques. We need ways to ensure AI explainability, understanding why the AI made a particular decision. We need to integrate AI ethics considerations into the safety case. It's pushing SSA practitioners into becoming data scientists and AI assurance specialists, too.
And connecting all these sensors and systems, that brings in another huge risk, doesn't it?
Cybersecurity. Absolutely massive.
How does that fit into safety assurance?
It's no longer separate. Cyber resilience is safety resilience now. If your automated signaling system or your train control network can be hacked or compromised.
The safety functions are gone.
Exactly. A cyber attack could potentially cause a collision or derailment just as easily as a physical component failure. So SSA practitioners now must incorporate cyber risk assessment into their hazard analysis. They need to understand threats, vulnerabilities, potential impacts, and ensure adequate cyber defenses are part of the overall safety case. We're assuring the integrity of data packets that command trains, not just physical wires.
The scope just keeps expanding. Now, with all this automation, you mentioned the human role is shifting more supervision, less direct control. What does the increased focus on human factors look like in this new world?
Well, as we automate more and more functions, potentially up to SI4, where the system is expected to handle almost everything,
We reduce the chance for manual errors, presumably?
yes, you reduce certain types of operational error, but you potentially introduce new, arguably more complex risks related to cognitive supervision and intervention.
Huh.
Think about it. If a highly complex automated system encounters a situation it can't handle, or starts to fail in an unexpected way, it might hand control back to a human operator who has maybe been passively monitoring for hours.
And they have seconds to figure out what's wrong and what to do.
Exactly, under immense pressure. Can they correctly diagnose a complex, unfamiliar failure mode? Can they take appropriate action in time? SSA now has to involve rigorous modeling of human reliability in these supervisory roles. How do we design the interfaces, the alarms, the training to support the human in becoming a resilient recovery mechanism rather than setting them up to be the final point of failure?
So human factors becomes about cognitive integration, error management under stress.
Human reliability modeling, designing for effective human system teaming. It's about ensuring the human can successfully supervise and intervene when needed.
Okay, let's talk about some of the big debates happening in the industry that our listeners might encounter. What are the major tensions or trade-offs right now?
Well, the oldest and most persistent one is definitely the trade-off between operational efficiency or throughput and the investment needed for thorough safety assurance.
Getting more trains running faster versus taking the time and money for safety checks.
Pretty much. There's always pressure on rail operators and project managers to increase capacity, improve punctuality, deliver projects faster and cheaper. But rigorous safety assurance, doing the full V model properly, conducting thorough independent reviews, resolving issues diligently, all takes time and costs money.
So engineers get squeezed.
Engineers, especially those in SSA roles, often find themselves needing to stand firm, using the legal requirement of SFAP as their justification, to ensure that necessary safety work isn't cut short due to commercial or schedule pressures. It requires technical confidence and sometimes political courage.
Okay, what's another big debate?
A really interesting one is about regulatory styles. Prescriptive versus performance-based regulation.
What's the difference?
Prescriptive regulations tell you exactly how to do something to be safe. You must use this specific type of axle, or your signal spacing must be exactly X meters. It's very clear, leaves little room for interpretation.
But maybe stifles innovation.
That's the main criticism. It can lock you into older technologies or approaches. Performance-based regulation, on the other hand, tells you what safety outcome you must achieve. Like your braking system must achieve a probability of dangerous failure no higher than 10 to the minus 9 per hour, setting a SIL target. Or your system must demonstrably reduce risk, SFRP.
And it lets the engineers figure out the best way to meet that goal.
Exactly. It allows for innovation, new technologies, more tailored solutions. The trend globally is definitely towards more performance-based or goal-based regulation.
But that sounds harder for the SSA person.
It puts a much higher intellectual burden on them, yes. With prescriptive rules, you just show you tick the box. With performance-based rules, you have to build a comprehensive, robust safety case, proving that your specific, possibly innovative solution actually meets the required safety performance level. The burden of proof is much higher.
Makes sense. And one final challenge you mentioned, responsibility in complex supply chains.
Yes, this is becoming huge, especially with increasing automation and integration. You might have one massive supplier providing the trains, the signaling system, and the control center software, a whole turnkey system.
Okay.
If something goes wrong in that integrated system, who is ultimately accountable? The RTO still holds the license to operate, so they have ultimate operational accountability. But tracing the root cause of the failure, was it a flaw in the supplier's software design, an error in their maintenance procedure, or something the operator did, becomes incredibly complex.
Forensic level stuff.
Absolutely. Allocating safety responsibilities clearly in contracts and having the SSA processes to manage those complex interfaces and potential failure points across huge supply chains is a major ongoing challenge for the industry. How do you ensure accountability doesn't get lost in the complexity?
Wow. We have covered an enormous amount of ground today. This SSA world is complex but absolutely vital. For our listeners, the engineering students, the early career folks, let's try and boil this down into some actionable takeaways. What should they focus on?
Okay, first and foremost, master the technical foundations. You need the tools.
Lite.
Become really proficient in RAM's analysis. Understand how to build a safety case, how to write a clear, evidence-based safety argument. Get good at root cause analysis. These are the hard, portable skills that make you valuable. If you can quantitatively analyze risk and justify safety decisions, you're indispensable.
Okay, technical skills first. What else? You've stressed collaboration a lot.
Hugely important.
Yeah.
So, second takeaway, elevate your soft skills. Seriously.
Why are they so critical in safety?
Because SSA is inherently collaborative and often, frankly, quite political. You're often the person translating complex technical risks into language that non-technical managers, lawyers, or operational staff can understand and act upon.
Bridging the gap.
Exactly. You need excellent communication skills, written and verbal. You need to be good at teamwork, negotiation, building consensus around safety solutions. Often, your ability to influence and persuade is just as important as the technical quality of your analysis.
That's a great point. Okay, before we wrap up, let's tackle a few common myths. Misconceptions that people new to the industry might hear and need to challenge. Got any?
Oh, definitely. Myth number 1, compliance equals safety.
Just ticking the boxes means you're safe.
It's a dangerous assumption. Compliance just means you've met the minimum legal standard laid out in the regulations at that point in time. True safety requires a proactive culture, constantly looking beyond the current checklist for emerging risks, for ways the system could fail that maybe the regulations haven't caught up with yet. Compliance is the floor, not the ceiling.
Good one. Myth number 2, maybe related to all the tech we discussed.
Yeah. Myth number 2, automation eliminates human error.
It doesn't.
It changes the nature of human error. It doesn't eliminate it. You swap potential manual operating errors for potential design flaws, software bugs introduced by humans, maintenance errors made by humans, or incorrect supervisory judgments made by humans. Human factors analysis remains absolutely critical, perhaps even more so, in highly automated systems.
Okay, shifting the error, not removing it. And a third myth.
Maybe the idea that we can engineer away all failure, that perfect safety is achievable through technology alone.
The zero risk fallacy again.
Exactly. You cannot engineer perfect reliability into complex systems indefinitely. Things will fail eventually. Good SSA isn't just about preventing failure, it's about designing for resilience. Meaning you anticipate failures, you design layers of protection, defense and depth, to catch failures when they happen, and you ensure the system fails gracefully, degrades safely rather than catastrophically. You design systems that allow for human recovery and intervention, not just assume machine perfection.
That's a much more realistic approach. So, wrapping it all up then, the core message seems to be that real, sustainable railway safety, true SSA success, isn't just about tech or rules.
No, it's built on the alignment of everything we've discussed. You need technically skilled, competent people. You need clear roles and responsibilities. You need rigorous processes that are actually followed, like the hazard management cycle. And underpinning it all, you need a strong safety culture, where safety is genuinely the priority, continuously managed, not just a phase you pass through in a project.
People, roles, process, culture, all aligned.
That's the goal. And for everyone listening who's entering or working in this field, remember that continuous learning is absolutely vital. The technology, AI, cyber, automation is changing so fast. The legal landscape adapts. Your own competency needs to keep evolving just to maintain the incredibly high safety standards rail has achieved globally.
Which leaves us with a final thought, a provocative question, perhaps for our listeners from all over.
Go for it.
Given this accelerating complexity, hyper-connected systems, autonomous operations, AI that learns in ways we can't always predict, how do we actually future-proof the human competency side of SSA? How do we ensure the engineers, the assessors, the regulators of tomorrow have the skills and understanding needed to keep managing these new, maybe even non-deterministic risks to maintain or even improve on today's safety levels? That feels like the defining challenge for the next generation of railway safety professionals.
It really does. A challenge and a huge opportunity.
Thanks for listening to Safe Tracks, the Systems Safety Assurance podcast. Here, we talk all about how safety assurance keeps our railways running safely, smoothly, and reliably every single day. If you're curious about RAM management, RAM analysis, and how reliability is actually calculated, check out the RAMs Ready podcast playlist on this channel. It's packed with great insights. And hey, don't forget to subscribe and tap the notification bell so you'll know the moment a new episode is out. Until next time, stay safe, stay assured. Thanks for listening to Safe Tracks, the System Safety Assurance podcast. Here, we talk all about how safety assurance keeps our railways running safely, smoothly, and reliably every single day. If you're curious about RAM management, RAM analysis, and how reliability is actually calculated, check out the RAMs Ready podcast playlist on this channel. It's packed with great insights. And hey, don't forget to subscribe and tap the notification bell so you'll know the moment a new episode is out. Until next time, stay safe, stay assured.